Hello guys, welcome to a new video. So in the last video we went through the OSI model on a very high level. There are many sorry about that. There are many terminologies and everything which we will go through eventually. But my basic objective with the last video was to get a basic understanding of how communication happen at a very meta level on the OSI model, rather than going into the terminologies, which we will eventually. But that wasn't the objective with the last video, because this involves a lot of things. We cannot just put everything into one single video. My purpose was to just give a basic understanding or a basic intuitive idea of the OSI model and connecting it to the real world communication. So yeah, after that, now what we have is, why do we need IP addresses? Let's discuss this. We discussed about the physical aspect of every device. MAC address is like, here we have the MAC address. MAC address is like the physical identifier of every device. Like every device has a unique MAC address, you can say, and basically you can identify a device with their MAC address. So rather than making it this complex, why don't we just cut through these 3 layers? We just put this data in the MAC address and send it through with the destination MAC address and maybe the source MAC address. It will reach the destination MAC address because every device is a unique MAC ID. It will identify it, and then it will send the message back. Why aren't we doing that? Why are we introducing this many layer of complexity when we can do the same thing without it? Which we can actually do. Let's say we have 2 devices. We can, if we know the other device's MAC address, then we can easily send data to other device from this one, and they can communicate with each other. So it's a two-way thing, let's say. But why aren't we doing this? Why are we using IP address and stuff? What's the purpose behind it? So this is a very simple use case. Here we have just 2 devices. Let's make it a bit complex. Let's say we have 4 devices, and let's assume it to be a network, if you may. Basically every device can communicate with one another. They have their unique identifier MAC addresses, and let's say device 1 wants to send something to device 4. How would it do it? So here, since there is just one level of one identifier, what device 1 needs to do is it needs to go through all the devices. It knows the destination, but for the message to reach there, it will have to send the message to all the devices that are in the network, and it will be hey, if you are this MAC address, then consume the data, otherwise ignore it. Which, from the very sound of it, sounds very inefficient, because even if with 4 devices it's somewhat faster, but if you assume it at a very high scale, if you assume the whole, every device in the world to be in one single network where devices communicate via the MAC addresses, imagine the amount of bandwidth that would be wasted, or energy that would be wasted in this, rather than forget about something else as per se. So this is not a feasible solution, so we needed something else. This is the same thing that we do with finding addresses as well. Let's say we have a world full of houses with specific identifiers or house numbers. Doesn't matter, not necessarily in a very sequential manner, randomly as per se, and we want to send something from one address to another, and the only thing we can use is the house number. Imagine how drastic would it be for the person who is delivering that thing. They can deliver it in they can just find a house maybe next to the first home, or it might take forever for them to find the house itself, because there is no other identifier. To find something, it's easier when things are grouped, and when you look for the groups, it's easier to narrow the search down. You may say, let's say you want to deliver something from Bangalore to Delhi. You cannot just put someone's house number there, rather than putting instead of putting city and everything and stuff, because even if you know it's in Delhi, or maybe you don't know, you're just putting in the house number. Imagine the extensive searching someone has to do to go to that particular place or find that particular house. So we tend to group things so that we can find them easily. So let's say you want to send something to Delhi, you put the Delhi. Now we have some specificity on where we need to look the data, where we need to look for the data. Then we put this maybe like city or landmark or anything. Like then we have more specificity of the data. Then we put the house number. Then we have more specificity. So as you can see, like we have a broad area to start with, which we need, because we cannot look for it in the whole world. We need something to start with so that it can be optimized. Inside that, we need further specificity. Inside that, we need further specificity, and we keep on moving until we find the place that we need to find. So that's an efficient method to look for something, which we also use in our daily lives. And it's not like you'll go through every single place in the world to find one single thing. Imagine your time and energy you'd waste in doing that. So why would that be acceptable with computers when you're just trying to optimize things? So that was out of question. That's why IP addresses came into picture. IP addresses have something called like, let's say there is a group of IP addresses and we call it a network or something. Then there are different networks in the whole world where there is something called subnet masking, which we will come into later. Basically, it's some terminology where you can, let's assume you have a city and you need to know if the place you're looking for is inside the city or in some other city. So subnet masking will help you with that. In the case of IP, if you compare it with a city or something, we'll come to that. But basically, for now, just assume that like it's sorted. If you want to like look for some, if you want to get to know that if the place you're looking for is inside the city or outside the city. So until you find it, you will just keep jumping cities one after another, like moving from IP address to IP address to IP address of networks and stuff. And when you finally find the city, then you go inside it and lower the level of, now you have lower level of searches. Like now you have more specificity on where to look. So you go on a very device level, you go through the IP address of devices, and then you have the IP address of a destination device, and then you just shove in the data there itself. That's the basic flow. Imagine a delivery situation, as I keep saying again and again and again. So you will go to a city, then you will find a landmark or a place name, then you'll find the house number, and so on. So same with this. Now let's one thing comes up is we compared IP address to city, we compared landmark, we compared a network with a city, we compared an IP address of devices with a landmark. Now what about the house number? So every device has like thousands of applications running. Similarly, like maybe near a landmark there can be many houses similar to that. You can somewhat visualize. We need the house number, and how would we get that? Let's say two applications are communicating. We need to get that destination application. We need to connect to that destination application properly, because there are many applications and processes running in one single devices. Precisely, there is a specific number of ports, which will come into later, but every port can have something running. So you can somewhat compare house number with ports here, if you may. Then you would know where to exactly go when you find that particular landmark or find that particular device. So that's like one layer below that specificity graph we have been talking about. Basically, first you scan through networks. Then when you find a network where the device lies in, you go inside, you scan through the devices. When you find the device, you like shove the message into the port that's defined here. And if you can remember, we already defined the port in the data that you're sending. Here we do it. Here inside the data grammar segment, we have the port, the source port and a destination port. So when inside the IP, basically you can assume it as layer of unpacking. When we are inside a network, we unpack this, we have this, we get the port, we shove it to the destination port, we get the data, we do the same flow again to return to the source, and that's how we get a response. So yeah, that's why we need IP addresses. Basic purpose is to narrow our search down so that we don't have this many wasted bandwidth or energy or whatever. so that we can utilize them in something else. And yeah, you can somewhat relate it to our daily address sort of a thing, how you tend to find your friend's place or some delivery guy tends to find the destination. It's somewhat similar to that. If you can visualize it, like we need some place to start with, then we just keep on moving down and decreasing the decreasing the search area one by one until we find what we are looking for. So yeah, that's the basic purpose that IP address serve. And yeah, that should be it for this video, I guess. I hope I was able to explain it properly. If you have any questions, you can always ask. I'll try to clear it down further if that's an issue. Yeah, that should be it for this video, I guess. See you guys. Bye.